This is a tool for working with Vyper called Moccasin. It's basically a full framework for like testing and debugging. It even has a console dealing with Vyper contracts. So the first thing we're going to do is just run mox install mox. Moccasin is a kind of snake, so all of our names are like snake names. So SnakeMate is kind of like a standard library. Well, it's a third-party standard library for Vyper. It's kind of like OpenZeppelin or Solidity or something. And so that installed everything in lib. And if you are super interested, you can be like, oh, like here's the files that it installed. So just now, I was saying that there's all these files that aren't really visible, right? So we've got my token. We have from like snakemate.tokens. Like this doesn't look like a token because there's a bunch of stuff missing. So where is all the stuff that's missing? It's in, sorry, here. Sorry, snakemate. Tokens, ERC20. So this is like the actual implementation. It's a library. And it has all these awesome functions in it. Ownership, mint, burn, yada yada. So let's say we want to actually do something with this. So we've like taken our token, we've like initialized it, we're like minting some stuff, and then the next thing we're going to do is like test it. So here's like some tests. Cool, right? Double check that the supply equals the supply. This is actually really awesome code that was not written by a human. So if we like run mox test, then it'll like test. Whoa, everything passed. That's actually incredible. So is there anything that anybody would like to see this token do besides just like, okay, you can like transfer stuff? Like a custom minting function.
ERC2612.
What is ERC2612?
Permit.
Oh, right. I think that actually might be available. So amazingly, we're saved by the bell because SnakeMate has a permit function. So what is in this interface? So interestingly, if we compile this stuff and look at this, it actually has a permit function in it. It's in the ABI. So the next thing, do you want to see anything about the permit function? Like, you want to test it?
Sure.
How do we actually test the permit function? I'm going to delegate that to you for now, so I can finish the rest of the, because I don't want to test this on the fly exactly. So the next thing we could do is, so in the Moccasin config, we've set up this Anvil network. So we're just going to run Anvil here. And, oops, mox deploy my token. So here, crap. I think this should work. Oops. something wrong here because Anvil wasn't even running. I think we can delete all of this actually. Where did this deploy to? Oh, we have to specify the network, sorry. Okay, and then we have to like make a private key and all this stuff. Mox wallet generate foo save password foobar. And then since we're in Moccasin, oops, Anvil run, private key foo. That's really not good, actually. Can I just use the private key that we made here? Okay, cool. So now we've like, sorry, this is an unfunded account, so everything failed. But it actually like generated this like deployment. So if it was like actually an account that had Ether in it or whatever, and I could like choose one of these things here actually that probably has some money in it. Oops. There we go. That's interesting. There's some kind of API mismatch now. But basically, it's very cool because the token like deployed, right? So if we wanted, we could actually like spin up the console and kind of interact with it. But I want to get back to you guys. How is that permit test going?
I am spinning up the console just the same as you.
Oh, okay. Before I continue, is there anything that anybody wants to see?
How would I go about checking that the allowance spending logic is correct? Because very common bug I see in ERC20 tokens is that when you spend the allowance, the arguments to the mapping are flipped.
Really?
I mean, I'm sure this is fine, but it is a basic thing I would check.
Yeah, so that's in here. So basically, this is a test for the allowance, okay? So, and then you just check that the allowance here, that's true, like the test and the implementation could like both be wrong, right? Who will test the tests, right?
Mutation testing time?
Very philosophical question. But I mean, it's quite straightforward because like after you like check that the allowance is there, then you like actually run the transfer from function, and then yeah, you check that the deducted allowance is like actually equal to the amount that you transferred. So basically, you would test it, and this this test is like all Python, by the way. Do we have more questions, or are you just kind of like interested to see where this is going? We could completely switch gears and go into track 2, which is like the optimizer, which is, okay, great. Some brave souls here. Which, in my opinion, is actually much more interesting. So I had Claude write this, right? So the track 1, it wrote in like 5 minutes, all of this like amazing code that like happens to work. And then with the Venom stuff, just to give you an idea how much more interesting or difficult it is, took like the rest of the hour. So, and I had to guide it a lot. So, let's look here. So the first interesting thing is that we can take a contract, a Vyper contract, and spit out the venom. So here are some interesting optimizations that we do. The first kind of pass of them. So obviously, like, these are kind of things that you might expect, but maybe also might not be obvious. So identity operations, x plus 0 is x, x times 0 is going to be 0. We have some weakening. These are called weakening. So like and or shifts are like cheaper on the EVM than like mul or mod, which are like 5 gas or whatever, 3 versus 5 gas. So where is this? Okay, so these are strength reductions. So these are nice algebraic identities. Let me spin up, make sure I'm in the right virtual environment. I'm going to close this. So, right, Vyper version, good. Let's delete that. So this is what the Venom, this is after all of the optimizations run, actually. So this is what the Venom code looks like. This is the entry into the selector table. It's super cool. You can read about it. We have a blog post about it. Blog.vyperlang.org. The constant time. So entry into a Vyper contract costs like, I think under 100 gas, if I am recalling correctly. And it's like constant. It doesn't matter how many selectors you have because of amazing hash table magic. Which is right here, actually. So anyways, this is the kind of the body of the main of the different functions. So this is the selector I'm assuming for, I wish there were more comments here. But what I'm going to do actually is going to turn off optimization so you can kind of see what it looks like. Oops. Run passes. What can we get away with not running? Let's just actually print it before running any optimizations. And this compilation is going to fail, but we're going to at least, oops. That didn't do what I wanted. Okay, so this is the unoptimized code. And if you compare with the source code, we're looking at, let's see, algebraic identities, right? So let's look for some XORs. That looks optimized. Sorry, technical difficulties. Oops. Okay, maybe that works. what is going on here? Yeah. Yeah, okay, this is the unoptimized code. Sorry about that. So there we go. So, right. For example, here we've got x is call data load 4, and then yeah, here, sorry, is call data load 4. So this is x or x, and here is going to be like x or 0 somewhere. But sorry, I'm like hallucinating. Okay. I see. I think maybe this example would be better if it were smaller. So let's try to like just extract some of these things. Turn C plus D. Okay, so this is a smaller example. So, right. And then so if we turn on the optimizations, or if we like examine what the optimizations look like before and after, sorry, what the Venom looks like before and after optimization, it will look a lot smaller. Sorry. There we go. Okay. So, what? Why does this look so unoptimized? Oh, that's interesting. We found a opportunity for more optimization, actually. I think. So I think what's going on is it's actually not running enough times. Sorry, that's really throwing me for a loop, because like this, the reason I've been like so confused is because this add 0 to 38 should be being optimized out, but it's not. So I think that's actually a bug, um, where the optimizer is being too conservative. I think we can take some other optimization passes though, that will also kind of be interesting. Okay, so this is an example of dead code elimination. So here, we generate a bunch of code for like this thing. So some of this is actually optimized a little bit in the front end. So we have this like constant expression, which is 260, and then we do blah, 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 you know, add, subtract, blah, blah, blah. So here, like, add 100 to this thing, and then we, like, store it in memory. But what happens after optimization is that all of that is, like, deleted. And then at the end, we just return 360. If we, I'm hoping that this demo world is going to work. So here's another kind of optimization pass. So this is the unoptimized code. Up here, we do all of this stuff. Sorry. Here, we allocate all this memory. We do a bunch of like, you know, arithmetic. So we can actually find where this gets reduced. Add. Yeah, so this is like, this one is actually folded in the front end. But here is like x times 16. There's going to be adding to 0, which is this thing. And then there's going to be like this modulo 8, which we can find here. And then we can find this like div 32. And then this whole experience is going to get a lot better if I actually print better things. So that's the final bytecode, by the way. So, man, we have. So x times 16 is going to turn into, I think, a shift left. So that's here. And then, let's see, mod is going to turn into this and thing, which is here. And then the div thing is going to be turned into a right shift 2. Yeah, this thing. So these are kind of like, these are called algebraic optimizations because they're just like things that can be done symbolically and you don't actually need real values in order to do them. Oh, I have 10 minutes? Okay. I want to look at some actual Venom examples. So this is like what it would look like if we took in straight Venom and optimized it. So these are like kind of actually more complicated. So SCCP is like sparse conditional constant propagation. it basically does constant folding and dead code elimination at the same time. So I guess what people used to do is they just like did those in a loop, but there's certain kind of things that you can't reduce if you just like loop doing like constant folding and dead code elimination. And I think this is actually one of them. Oops. Yeah, this is one of them. So this is like something where basically the loop condition like depends on like the constant propagation at the same time. So if you like stare at this long enough, maybe you'll have an epiphany about like how you could optimize this. But we're actually going to use the Venom binary. Great. Workshop. And, oh, shoot. Okay, now we have to fix all the compilation errors. All these labels should, in the syntax, look like this. Right, so this is like what it's supposed to look like afterwards, and we'll just comment that out. Oh, great. None of this is compiling. Sorry, this is a very bad demo because it's like not compiling. And I'm wondering if it's something that was introduced recently. Oh, return. Let me see. mstore 32i return 3232. There we go. So if we actually print the thing after SCCP, it doesn't look like all of this. It looks like much smaller. Basically, a lot of these branches have been like eliminated. And this is like actually kind of a non-trivial example, so you can like take it and kind of work through it with pen and paper actually, because it's like, it kind of gives you an idea of what it does by like actually working through it. Okay, and I think we're about at time.
Yeah. Have a question?
I was gonna ask, please, though. Okay. Might be a dumb question, but what's non-trivial about your example?
What's non-trivial is if you like keep propagating this constant. Let me see if I can actually like find where it is. I think the control flow graph is like too complicated because like, basically the thing where it gets, okay, so what I was saying is like you do constant propagation and dead code elimination in a loop. So if you do that here, you can't like eliminate the code where it gets assigned something else. So, oh, sorry. So there's some variable which gets assigned something different in two different branches.
Oh, okay.
And if you like, yeah, do it in a loop, then you can't like eliminate the branch where it gets assigned something else. Okay? So then like, yeah. So by doing them at the same time, basically, or by following the SCCP algorithm, it like, how do you explain it? It like does the evaluation in parallel. It like evaluates the values symbolically, but it also does dead code elimination at the same time. So it like sees that you can't like recurse into the branch that's not taken. So then the J or whatever never gets assigned the other value. So it can prove that it's always a single value rather than like it takes different values in the branches. You have any questions?
Question?
Thank you for the workshop. You mentioned before that you have constant access time to the selector table.
Yes.
How
Do you want the long answer or the short answer?
you choose?
So I think everybody knows how Solidity does it, right? It's like a branch log2 or n log n or whatever. It's a binary tree. And that's like not the only way to traverse data, right, that we know. There's also like hash tables. So I looked into this a long time ago, and basically the problem with hash table is like you end up having to loop, right? So if you think about like evaluating this hash table, you have the traditional way would be like you have some data in memory, right? And then you have the query, the key, and then you like look at the bucket where it is, and then you loop over the bucket and probe into it. And the problem with that is like jumps like basically suck. Loops on the EVM suck. So if you do that, then and you're like reading this thing from memory in a loop, then it's actually really inefficient. So it's like 0.1, but with a really high constant factor. So there's a couple tricks that we do, but the main thing is like we transform this hash table into a code data structure. So the bucket is a location in the code. And then instead of like traversing code, instead of traversing data, like the thing in memory and load and loop, you traverse the code. So what it ends up looking like is the ERC20 example might actually be a good example. I'll do both IRs and see which one is easier to keep track of. Sorry. One source token. So if we go all the way to the top where the so you jump to these buckets, which are actually represented in the code. So if we look at what's in bucket 1, oh, of course. It's just a sequence of if statements, actually. Yeah. So like normally you would have the method ID in like memory, and then you like probe and check equality to this method ID every iteration of the loop. But instead of using the initial hash to look up a bucket, you use it to look up a section of code, and then you just traverse into the code. And then the code there is very simple. It's just a sequence of if statements. I don't know if that answers your question. But basically, it converts the data structure into a code structure.
Okay, so in the end, you have less if statements instead of.
Yeah, and there's some tuning too. So we like simulate a whole bunch of possible code layouts for the selector table, and then pick the one that has the lowest variance in the probe depth.
Okay, okay.
Yeah, and so the average probe depth is like 1 or 2 if statements, and in very like weird, very what is the word? Pathological cases, it can be like 3. But I did a lot of tuning of this. The probability of that is very low. We basically iterate through a bunch of hash functions, where the hash function is basically defined by a number that you have the initial starting modulus from, basically.
Thank you.
Yeah, yeah.
Any more questions?
Thank you for bearing with this incorrect format talk.
You try to. It's important.
Yeah.
To try this type of thing.
Yeah, yeah.
So thank you for that.
Yeah, anybody who wants to come talk to me or like actually go through the workshop like interactively, like, please. My Telegram and Twitter are big_tech_sucks, SUX. Or the official Vyper Lang Twitter, Vyper LANG, VYPR. Let me actually just pull that up. That's how you know you found me. Cat.
And thank you for what you do at Vyper.
Yeah.
Especially for when we do like advanced math.
Yeah.
That costs a lot. No, I think everyone.
For the record.
And I think like when you do math in general on chain, that costs you a lot, and Vyper apports like really important vision, important library for every like DeFi and mathematical community. So thank you for what you do in general.
Yeah. And one thing we're working on is like getting more DeFi building blocks as libraries. So like if you want to build a lending market or a DEX, like it's kind of, there's some source code available and you can just like adapt it. Yeah.
Great. Thank you, Charles.
Okay, yeah, thanks.
Yeah.
Thank you very much.
Thank you very much.